For those who don't know me, I'm from the University of Maryland, the United States, and I'm the chair of the Cyber Regional Program in IMBeR, and I will be your convener for our plenary session today. Before we start, here's a quick announcement. The posters, the old posters from yesterday, need to come down at the coffee break if you haven't already taken them down. And the new posters need to go up during lunch for this afternoon. So, moving on to our plenary session, the motivation behind today's plenary session is to highlight IMBeR achievements and specifically progress toward advancing the IMBeR research themes. Yesterday, Eileen reviewed the IMBeR research themes in her plenary presentation. Recall that Theme 1 is interactions between biogeochemical cycles and marine food webs. Theme 2 is sensitivity to global change. Theme 3 is feedbacks to the Earth system. And Theme 4 is responses of society. Our first presentation today is by Dr. Coleen Moloney, and she will address IMBeR Research Theme 1, interactions between biogeochemical cycles and marine food webs. Coleen is the director of the Marine Research Institute at the University of Cape Town, South Africa, and an associate professor in the Department of Biological Sciences. Her main research interests are in the variability and dynamics of marine food webs and ecosystems under global change. Coleen uses modeling studies to try to understand the complex interactions and feedbacks among physical, chemical, and biological processes in marine systems. She has been involved in IMBeR since its inception as a founding member of the IMBeR Scientific Steering Committee, and she was one of the editors of the IMBeR Science Plan. In her presentation today, Coleen will review some approaches and advances in modeling marine biogeochemistry and food webs that have emerged during the IMBeR program and discuss some of the questions that are being asked and answered with these models. Coleen.
Hey, am I switched on? No.
That's it.
Switch off. Yes? No? No? It's just okay, can you hear me? Yes. Okay, good morning everyone. I'd like to start by thanking the organizers for inviting me to give this presentation at the IMBeR Open Science Conference, and also for giving me the opportunity to visit Bergen. Beautiful sunny city where it never rains. My presentation is quite broad this morning. I'm covering quite a lot of territory, and so I'll be skimming over many aspects, and I'm being quite selective in what I present. So I'm going to try and concentrate on some past research in modeling marine food webs and biogeochemistry, and then use that as a basis for looking forward to the future. The presentation is structured around 5 questions, and I'm going to start by asking which models were used for this purpose and why were they built. IMBeR is a very broad project, and one of the goals was to try and link the processes from ocean physics through marine biogeochemistry to food webs. Obviously, this is a very complex set of processes contributing, and one of the tools that, or the primary tool for trying to do this is the use of models. And the models that were developed for this purpose, I'm referring to as end-to-end ecosystem models, and they really aren't models by themselves, they're modeling systems, because all of these models are linked together, either through information transfer or by connecting the models, a series of modeling of different model types. So typically an end-to-end model will have some kind of a hydrodynamic model that represents the physics of the ocean. That will be linked to a biogeochemical model, which has the goal of trying to figure out how the elements in the Earth system are transferred and repackaged between living and non-living forms. And this typically takes the form of a nutrient, phytoplankton, zooplankton, detritus, an NPZ model, or a model of the lower trophic levels of the food web. And then that model is connected to an upper trophic level model, which extends the food web often all the way through to top predators and increasingly to humans through fishing. So that's the basic form of an end-to-end ecosystem model. How many of them have been developed? Well, I did a very quick Google Scholar search, and just using a search term on marine biogeochemical model, this is a cumulative plot of the search results. So obviously these aren't all publications, but this gives an indication of the field, and it's sitting at about 6,500 results. When I did a separate search looking at using the search term marine ecosystem model, that yielded about 3,000 results, and when you put the two terms together, there are about 1,000 results. But the interesting aspect of this to me was the exponential growth that is evident during the lifespan of IMBeR. And I think it illustrates one of the successes of IMBeR, which is that... Uh-oh. Okay, am I back? Yeah. Yes. IMBeR and groups like IMBeR have been really important in stimulating and guiding the research on end-to-end ecosystem models. And I've got a series of success slides that are going to run through my talk's achievements, and I think this has been a really important achievement of IMBeR. There has been considerable international effort in developing end-to-end ecosystem models, and there has been excellent progress in linking and nesting models, definitely in the technical ability to do that kind of linking. So there are many, many end-to-end ecosystem models today, and I'm not able to cover all of them, and I don't even know all of them. So what I'm doing through this presentation is just taking a selection of some of the models that I'm familiar with and using those to illustrate some general points. What questions were asked and answered by these kinds of models? Well, I found that one could really group the different aims or hypotheses or objectives of the end-to-end models into two broad categories, which was quite interesting. I was expecting there to be a much bigger range of topics that were addressed. Two general questions. The first, what are the effects of the environment as a bottom-up forcing and fishing as a type of top-down forcing on marine ecosystems? And the second question, what regulates patterns of biodiversity in marine ecosystems? The first question illustrated to me, and especially in the most recent modeling studies, another achievement of IMBeR, which is that it has forced people to start looking at some of the multiple factors that are influencing marine ecosystems, rather looking at factors in isolation, and particularly when it comes to the impacts of fishing, to understand that fishing doesn't operate by itself, but it's operating in a changing world. So this is the first example of an end-to-end ecosystem model. This is a model system that was developed by Morgan Travers and Yun Shin and their colleagues. And here it's being applied to a coastal upwelling ecosystem in the southern Benguela. The model system uses the regional, I can't remember what, ROMS as a physical model. The biogeochemical model has two components for each of these N, P, Z, and D. And the upper trophic level model is called OSMOS, and that is a fish community model that is size-based and is stochastic. And so it is a model where the properties of the model emerge as the dynamics are progressed forward in time. This model system was used in a series of experiments that examined the combination of 5 different climate scenarios and 5 fishing scenarios. For the climate scenarios, the wind forcing was altered. So the winds were either decreased or increased by multiplying by a factor from 0.4 to 1.6, where 1 is obviously a baseline situation, and 5 fishing scenarios, where just the top fish predators in the model were subjected to increasing levels of fishing mortality. And then the results, I'll just give you some of the results that they presented. This is an example of a result for the phytoplankton group, where the influence of the wind is illustrated along the 1 horizontal axis. The influence of fishing is on the 2nd horizontal axis. And in the vertical, you can see the changes in the biomass relative to the baseline. So where the boxes are blue, the biomass is increased, and where the boxes are red, the biomass is decreased. And the baseline, this is now the model results for 4 different aggregated groups: phytoplankton, zooplankton, small fish, and the top predator fish. The baselines are indicated with the circles there. And if you first consider the bottom-up effects of the wind forcing, you can see that there is a bottom-up effect that is propagated through the ecosystem to the top fish predators. So increased productivity results in larger fish productivity. For the top-down fishing effect, which is shown by the orange arrow, there is a cascading effect. So as the top predator fish increase in biomass, so their prey decrease, the zooplankton increase, but that effect does not propagate all the way through to the phytoplankton. And then I'm not going to go into detail, but if you blur your eyes and look at the blue and the red patterns, you can see that the phytoplankton and the fish boxes look quite neat, but the zooplankton and the small pelagic, there's a lot more going on in those scenarios, indicating the complexity of the interactions in the food webs. Okay, so moving on to the second example for the second question. These are the models that are looking at biodiversity patterns in the ocean. And this is a modeling approach that is quite recent, pioneered by McFollows and his co-workers through the classic paper that was published in 2007. And really is a modeling approach that is based on the use of trays. Different trays, the models themselves are self-organizing, they are adaptive, and they are stochastic. The idea in these models is that first principles are applied to a system, and you look to see what evolves in the system. I'm going to give an example of the application of this kind of model from the paper of Barton et al. Published in Science in 2010, where they were asking the question, does marine diversity decrease with latitude and why? So this is one of the model results. And what has happened here is this is the application to the global ocean. A hydrodynamic model provides a virtual ocean in which virtual phytoplankton are released. Each phytoplankton is assigned randomly a set of trays, which allow it to cope with different environmental conditions, but means that it's adapted to a specific suite of conditions. And then that model is allowed to evolve, and the results show what kinds of phytoplankton occur in different parts of the ocean. These color codes are just for an index of diversity, and you can see that the question they asked, whether diversity changed with latitude, yes, there is higher diversity at the equator, lower diversity in the high latitudes, but with some patchiness. And the causes of that diversity, because this is a model, you can go and examine what's causing the patterns, and that was attributed to dispersal and to seasonal variability of the environment. And this is a really good example of the use of first principles modeling to try and help us understand the processes occurring in the ocean and the trade-offs among different trades in the organisms in the ocean. And it also illustrates an achievement of IMBeR, which is, or IMBeR and like-minded programs, which is that there has been a whole variety of new modeling approaches developed over the last decade, of which the tray-based approach is one example. And there are a number of presentations at the conference illustrating these approaches. In contrast to models that are developed for understanding, and that is one of the goals of IMBeR, there is also a need to try and predict future states of ecosystems. And there is always a tension between models for understanding and models for prediction. Because models for understanding, one tends to want to have as much detail as possible in those models, because we don't really know which processes are important when. And that allows one to do long-term scenarios to see what might happen, but it's also a little bit unsatisfactory because those models can give you anything you want. They're not really well constrained because we don't have large enough data sets to be able to use those models cleverly with data. The statistical empirical approach is an approach that relies on data. And those models are more honest because they are being constrained by data, but they are also limited because it's dangerous to try and extrapolate those models beyond the range of the data. And we all know we're living in a changing world with a changing ocean, and there are conditions in the ocean that probably haven't occurred before. So we need to find a balance between these two approaches. One of the achievements I think has been happening in the last few years as people are moving more and more towards the predictive kind of modeling is that when you are doing predictions, you also need to be concerned with uncertainty. And I think there has been quite a large development in actually quantifying and reporting the uncertainty associated with ecosystem models. 15, 20 years ago, well, I still do it, but most people, when they model, you'd produce a result and you'd look at a picture of some data. And that was as good as the fits were. Now it's much more quantitative, much more rigorous, and a number of different approaches are being applied side by side. So how were the models applied in terms of understanding and prediction? Well, there's a bias towards models developed for understanding, which is in itself understandable, because most models are actually still in stages of development. So we aren't quite at a maturity stage where we're able to use models for predictive purposes mostly. But there are also examples of cases where the two approaches, the first principles and the statistical empirical approach, are being combined. And in those instances, there's some really interesting results that are emergent from that kind of way of modeling systems. And this is an example from the Chesapeake Bay Ecological Prediction System, which is a modeling system that essentially uses a physical biogeochemical model, a first principles model, to produce variables that represent Chesapeake Bay. And those variables are things like temperature, salinity, chlorophyll, nitrates, and oxygen. So the basis of the environment is produced by a model, and then a previously constructed statistical model, a multivariate statistical model, is used to give results about the probabilities of different harmful phytoplankton species occurring in different places. So this is a result from the application of that model. The two left panels are the results of the first principles model, which are predicting the environment. And the larger panel is showing the probability, low, medium, and high, of having toxic or harmful species in different regions of the bay. And this is used for 3-day forecasts and nowcasts, so very short-term predictions for the future. A second group of models are the models of intermediate complexity for ecosystem assessments, mice. These models have been developed to target specific questions or management objectives. And they're quite restricted in that way, in that they are designed for a purpose. I'm just going to give one example that came from a recent publication from Eva Plagani and her co-workers, where they were looking at the direct and indirect impacts of site-specific catches for large pelagic fish species taken by commercial longliners in a system in Australia. And this modeling approach recognizes the complexity of ecosystems, and it divides the whole social ecological system into different components, and there are 5 represented here. So there's a physical component in blue, an ecological in green, a human component, some anthropogenic effects through fishing mortality as pressure, and some management aspects. So this is the complexity of the whole system. But when the MICE is constructed, what is done is only those aspects of the system that are important to the question are selected and put into the model. And the model is then constrained with as much data as is possible. Typically, normal fisheries stock assessment data are used and other supplementary information. This model is also a really nice illustration of one of IMBeR's other achievements, which is the increasing inclusion of the human dimension in these models. And this is illustrated quite nicely in the way management and human components have been linked to the system, in the system. So the human dimension has been a developing focus in IMBeR, and it's also filtering through to the end-to-end models. So what are some of the gaps? Well, there are always gaps. Modelers always want to put more stuff into their models. I'm just going to highlight 2 that are linked to neglected trophic processes. The first is mixotrophy. We tend to work with NPZ models, phytoplankton and zooplankton, and this is the classic view of what our view of the food web has been. You have photosynthesizing phytoplankton, and you have zooplankton that eats other things. There was a workshop on Monday at the conference that looked at mixotrophy, and what is emerging is actually a lot of the protist groups are not pure photosynthesizers or particle ingesting organisms. There is a spectrum where things that you think are photosynthesizing actually go out sometimes and eat other cells. And things that you think are animals actually sometimes are going out acquiring chloroplasts and photosynthesizing. And this really raises the question of how important is this now? How is it going to affect our current models? And when and where do we need to include mixotrophy in those models? I think it's a really exciting field that is open for opportunities. The second process is parasitism. I've been giving foodwork talks for a while, and I'm always asked about parasites. So I thought, well, I better go and look into parasites because someone's going to ask me today as well. And parasitism is neglected because parasites are really small, and their biomass is negligible in ecosystems. So we've tended to think that they're not really important. But there are groups around the world who are looking at parasitism in food webs. This is a result from the application of a food web study to a salt marsh in California. And the first thing I noticed when I looked at this result is that the food web is being represented here with the nodes between the connections being species. And most of the people who are working in IMBeR, when we model food webs, we don't use species, we use functional groups. So this makes the food webs very complex. But the species approach is important because parasites are species specific. So this is a subweb in that system. When the parasite part of that is added, you can see the enormous number of linkages that are then brought into the system. And there are, I think, 2 aspects of this that are important for the kinds of studies that are done in IMBeR. The first, if you're considering diversity and you're looking at diversity and stability in ecosystems, I don't think you can really ignore parasites. They do have a role, they do come into play at some stages, and they are increasing the diversity of the system enormously. The second is I don't think we really understand when parasites might actually act as triggers. So it is possible that in high density situations, things like disease could be a trigger that turns the system from one state to another state. And that's a hypothesis. It would be great if there were some studies that could go out and actually start looking to see whether there is a role for parasitism in these food webs. So, looking to the future, my view is that at the moment there has been considerable development in our technical skills in modeling end-to-end ecosystems. I think it has matured very rapidly. But I think that the scientific understanding is of necessity lacking that technical development. And I think we are still in the infancy stages of trying to figure out how to use the models, where to use the models, and what is possible and not possible with these models. I think that what might be helpful is some clear guidance around some focus questions as we move to the future. Focus questions are really useful in that they help promote global collaborative efforts. They also help with the comparative approach, which I think is a really strong approach and has been illustrated in quite a few of the talks that I've actually been to through the conference already. So my plea for a future direction is to perhaps identify more focused questions that the global community can hang on to as they plan their research in different regions. And a cautious approach. We need to be careful not to overpromise on what the models are able to deliver. But the devil on my shoulder is also saying that we can't just be cautious and take things slowly. We also need the bold and the adventurous to leap into the unknown. Because I think in order for science to progress, we need to have people who are willing to take chances and to fail spectacularly as well as triumphantly succeeding. We need to make progress. We can't all be followers. So we also need those pioneering people out there who open up new ways of doing research. So a little bit of, a lot of caution and a little bit of adventure. Thank you very much.
Great, thank you, Coleen. We have time for some questions from the audience. KK? We have a mic, KK, hang on.
I just want a clarification. In your mice plot, there is both human and also anthropogenic effects. And what's the difference between the two?
I'm not an expert on the study at all, but my interpretation was that the anthropogenic effects refer to the forcing factors, and the human effects were contributing aspects of the system. I don't know. Yeah. So I think it was just separated. Yes, I was looking for you.
Yeah, so basically the anthropogenic was the direct effect from the fishery, whereas the effort allocation came through the human dimension, so it was the way that came forth. Thank you.
More questions? We have time. Ah, there's somebody. Oh, that's John in the back.
Coleen, very interesting talk. Thank you very much. I'm Andy Constable, with the predictive models, and I realise that they're very challenging to make suitably confident to be able to use the policy data. But you think that they're now at a stage where they could be telling us what we should be going to measure in order to be able to identify how good those predictions are, so we can start to run the system.
I think on a small scale, one of my hopes when I was preparing for this talk and going through models was I would be able to come up with some harder recommendations. What I'm finding is that there are a lot of studies happening all over, and they're very specific, and they're coming up with results that sometimes are similar to other systems and sometimes different. And so it's quite difficult to step back and say, yes, this is what you need to do. I don't think that the end-to-end models are doing better than other models in making predictions into the future. What tends to happen is a model is developed and we're still trying to understand how it's working and not necessarily able to say this is what information is needed. Because it's easy to say we need more data, and that would be the easy answer, but you need to be more specific, and I don't think the models are quite there yet. That's just my opinion. Others might differ.
More questions? We got time.
Thank you very much. That was very interesting. I wanted to get your opinion of how well we use what we know in order to evaluate our models. If you have a long enough data series and you don't have good enough data, do we use retrospective analyses sometimes to understand how well our model is working? That's one question, and the other is the extent to which the effect of cannibalism might be incorporated into food web models and fishing source of removal.
Okay. So yes, data are used to go retrospectively to try and predict backwards, essentially what has happened in the system, and that's often the most common use of data with models. There aren't enough and long enough time series, and in many instances, but that's a very effective use of data and models. The second question about cannibalism. Cannibalism is notoriously difficult to incorporate in models because it's an interaction as opposed to in a component, but it is included and it is considered. It's perhaps best considered in the marine environment in size-based models because their species and functional groups are split among sizes. But certainly cannibalism is a process that is considered.
So that's incorporated in the principles of natural mortality?
As predation mortality, yes.
Any other questions for Coleen? Yes.
Thank you very much. Olivier Moret from IMBeR, South Africa. Thanks, Coleen, for this great talk. It was a great overview. As you point, the role of data is essential for progressing in the development of end-to-end models, because of course we lack a lot of knowledge about the processes at the basis of the functioning of this. And I think we have to recognize that there hasn't been enough collaboration between field scientists and modelers, on that we usually do not work together. We are in quite separated communities. So how would you see the role of IMBeR in trying to stimulate this collaboration so that both observationists and modelers could work in the same direction together?
Thank you. That's a really good point. The role of IMBeR, I think IMBeR has had great success in its working groups. I do believe that focused working groups that are set up in such a way that require involvement of those field biologists, experimentalists, and modelers is one way of trying to tackle something like that. If you have the same question that you're trying to answer, with different tools to answer it, that is a way of fostering that kind of collaboration.
Any other questions? All right, well, let's thank Coleen again for that excellent talk. Okay, moving on. Our second presentation today is by Dr. Jean-Pierre Gattuso. He will address IMBeR research theme number 2, sensitivity to global change. Jean-Pierre is a research professor and director of research at the Laboratoire of Oceanography in Villefranche and at the University of Pierre and Marie Curie in Paris, France. His main research activity relates to the study of the cycles of carbon and carbonates in coastal ecosystems. Jean-Pierre has been working on the response of marine organisms and ecosystems to ocean acidification since 1995. He was the scientific coordinator of the European project on ocean acidification from 2008 to 2012. Jean-Pierre was also the founding chair of the SOLAS IMBeR Ocean Acidification Working Group, and he is a recent past member of the IMBeR Scientific Steering Committee. In his presentation today, Jean-Pierre is going to review current knowledge of the threats posed by ocean acidification to marine organisms and highlight key unknowns and research gaps. Jean-Pierre.
Thank you very much. Am I connected? No. Thank you. And thanks to the organizers for inviting me. It's a great pleasure to be here today. After I prepared this talk, I just looked at the banner of this meeting, Future Oceans. And I looked at the keywords which were on the right-hand side, and I said, well, multiple stressors, I got it in the presentation. Drivers, yes, I'm going to talk about drivers, challenges and solutions also. So I should be okay for this talk, I hope. I am addressing all the key words of this meeting. Before I start, this talk is focused on ocean acidification, and I really want to insist about the multiple drivers. Ocean acidification was born as a research field a few years, maybe 10, 15 years ago, and has focused on this very particular predator. But obviously, and as Nikki Grubler indicated yesterday, pH is not the only driver that is going to change in the future. Temperature is going to increase quite a lot. Here, projections shown here using two RCP scenarios, 8.5 in red and 4.5 in green. And at the surface in the continuous line, and at the bottom in the dashed line. So temperature is going to increase up to 3 degrees or more. Oxygen is going to decline, although quite a moderate decline globally. And pH is going to decline by 0.2 to 0.4 units or so. So that's a very important consideration, and most perturbations experiments so far, and I will address that later, have only focused on ocean acidification, which is a kind of a problem. So the drivers of ocean acidification, by far the main driver of ocean acidification is CO2 emissions from the burning of fossil fuels and the manufacture of cements. That's true in the open ocean, but in the coastal ocean, that's not so true. I mean, there is a significant contributions in local places from nitrogen and sulfur deposition along the coastline, especially in European areas in the north, and also in the coastal areas. The input of organic matter through rivers is a key contributor in some places of low water pH along the coast. And finally, there is the upwelling. Upwellings also provide low pH water, mostly in coastal areas, which led to significant problems in the US. Our US colleagues have worked quite a lot along the coast of Oregon and Washington State. And also, Nikki highlighted that yesterday, and Dick Philly and colleagues have shown that this low pH water is reaching the coastline, very shallow waters, including up to the surface, leading to major problems for the oyster industry. So that is also a significant contributor to acidification. Before I continue, I'd like to make sure that you have heard about Slow Science. Slow Science is an organization which was established in Austria, and now I think it's based in Germany. And this Slow Science organization is modeled on the Slow Food organization. And if you have seen this logo sometimes in restaurants, it's a fantastic concept whereby the restaurants are using only local products and also use traditional recipes. So based on this slow food thing, some colleagues have launched this slow science organization, and they argue that we need to take time to think and read, as opposed to what we increasingly do, need to find money and publish as much as we can. So that's slow science. Certainly, ocean acidification is not slow science, at least in the recent years. This, on the left, you can see the number of papers published every year. So the first paper we identified, of course, at the time we didn't mention ocean acidification, is 1906. It's even before the pH scale was invented by Sorensen in 1909. And at the time, some marine biologists were looking at the impacts of acids and bases on biological processes such as the reproduction of sea oceans and things like that. And then in 2004, a meeting was organized by UNESCO in Paris. That was the first meeting of the oceans in the high CO2 world, 2004. And then really the field rocketed, and you can see this tremendous increase in papers. Just last year, 530 papers were published on ocean acidification. This year, we are in June, and it's about 200. So the field has increased a lot. And the number of authors also is tremendously large. In the late 1990s, maybe 10 of us were looking at the impacts of ocean acidification, mostly on corals and on calcification. And now, a total of more than 4,000 scientists have published on those issues. So it's definitely not slow science. And if we look at this curve on the left, 50% of the papers have been published in the past 3.5 years. And only on biological responses, 1,500 publications. So there is, in this presentation, I could not possibly, go through specific papers. So what I have tried to do is to provide an overview, an overall assessment of ocean acidification based on recent synthesis or assessments. So despite this flow of information, there is a big challenge, and it's a paradox that Scott Doney has illustrated this way. Here on the x-axis we have time, and on the y-axis confidence. And initially, in the late 1990s, maybe 2000, we were here. We had looked at the impacts of OA on corals, tropical corals, coralline algae, and we felt we understood everything. It was clear and simple, a high degree of confidence. And then, starting 2004, 2005, 6, 7, as the number of publications came out, various processes were investigated, we really lost a lot of confidence because we had conflicting results, no effect on some organisms, some effects on others, so very specific differences. And then I hope that now we are in this recovery phase where we are gaining a little more confidence through those assessments and meta-analysis that have been performed in recent years. So, in fact, there is, of course, a risk when there is so much information to provide misleading information to decision makers. I remember when EPOCA was launched in 2008, the European Commission was basically asking us whether there was a tipping point. We don't want to pass a certain threshold of pH in order to avoid the detrimental effects on the society and the economy. So they wanted this magic tipping point thing. And with all this flow of information, it was extremely difficult to come up with some sense of the impacts on some processes and key organisms. So now it was time to go to slow science, to slow mode, and try to think, sit with, think and do some synthesis activities, evaluate this enormous body of literature, and try to organize the knowledge in a way that is useful to the scientific community, but also to policymakers. So in recent times, several attempts have been made to synthesize. One of them is this book on ocean acidification, and then we performed a survey as part of an IPCC meeting in Okinawa, an expert survey on ocean acidification. And then last year, 2013, two meta-analysis papers were published, one by Whitman and also Kroeker, and the other one led by Kroeker. And also last year, 2013, following the third meeting of the Oceans in High CO2 World, this on the top right, this summary for policymakers was published by IOC, UNESCO, SCORE, and IGBP. And finally, just this year in March, the Working Group 2 report of the IPCC has been released. And overall, in the two working groups of the IPCC, I could find 14 experts on ocean acidification, and several of them are in this room at this meeting. And that doesn't include the contributing authors. There is also a list of experts. So even though in AIR 4, ocean acidification was not well covered at all, it was just very briefly touched. But in Working Group 2, in AIR 5, ocean acidification is extremely well covered. In Working Group 2, on impacts, it's covered in at least 3 chapters, the coastal ocean chapter, the open ocean chapter, as well as the regional ocean chapter. And in addition to that, there is a cross-chapter box, the one on the top right, which is cross-cutting across several chapters of the report, and also there is a box in the technical summary that's 500 words on ocean acidification. So meta-analysis. I'm going to, in fact, mostly focus now on a meta-analysis of Kristi Kroeker, as well as on this summary for policymaker that I mentioned. The problem of meta-analysis, a well-known issue of meta-analysis, is the publication bias, whereby non-significant results may be more difficult to publish than significant. So when you do a meta-analysis, of course, I mean, your analysis could be biased because it doesn't include all results on a particular process. And this has been used just a few days ago when a special issue of ICES, Journal of Marine Sciences, has been launched. And in this in the text that goes along with the launch of this special issue, the editor argues for a publication bias in the ocean acidification literature against studies showing no effect of OA. So that would be a kind of a problem. I'd like to point out that in the paper I'm going to discuss, the meta-analysis that we performed with Kristi Kroeker, we ascertained that there was no publication bias by looking at the number of not significant results that would need to be added to change the significance of the analysis. That's the horizontal set number. And this number was large for all the analyses that Kroeker et al. Performed, suggesting that the results are robust. Also, what Kroeker did, she looked at the effect of removing one experiment that provided a large response ratio or a large effect size, and see whether the significance was affected by a single paper. And it was not the case. No changes in significance were found by removing the experiments with large effect size. So I don't think, at least from this meta-analysis, I don't think that the publication bias is a significant issue. So Kroeker looked at various processes which are listed at the bottom of this plot: survival, calcification, growth, photosynthesis, development, abundance, and metabolism. So what we see on the y-axis is the log of the response ratio, the effect size. So when this number is above 0, above the dotted line, the effect is positive, the effect of ocean acidification is positive, and when this number is negative, the effect is negative on that particular process. And what we see in parentheses below each point is the number of papers involved, number of experiments involved. For example, 69 for survival. As you can see, there is a significant negative impact of ocean acidification on several processes: survival, calcification, growth, development, and abundance. But that's a global number. I mean, it looks at all the taxa. When you look at what happens within certain taxa, and here there are two illustrated: calcifying gas, glycophores, etc. The first thing you'll notice is that there are a lot of gray color. The gray color is those processes have not been tested in those taxa. For example, for fish, there are quite a lot of processes that have not been investigated in the context of ocean acidification. What we also see that there is a little bit of green. There are some winners. For example, growth of fleshy algae or growth of diatoms is overall stimulated by ocean acidification. There is quite a lot of pink. Pink is a negative effect, so that is below 25% reduction. As you can see, calcification is one of them, growth in certain taxa. And also the red color shows a negative effect that is above a reduction of 25%. Again, calcification for corals, for example. So there is a lot of differences depending on the processes and the taxa, which makes it difficult to summarize all this amount of literature. Oh, I forgot the yellow color. No effect. For example, crustaceans overall seem to be quite resilient to ocean acidification. Again, against this, it doesn't mean that all species behave the same. There are exceptions in the literature, but statistically, this effect is not significant when we compile all the data. So now if I turn to this summary for policymakers, which was published last year by SCORE, IOC, and IGBP. We gave confidence levels to certain statements. So the confidence level are 4, very high confidence, high, medium, and low. So for each of the statements, you will see one of those logos, V, H, M, or L, indicating the level of confidence. So for the chemistry, you see that we have 3 statements here and 3 V's. Very high confidence that anthropogenic ocean acidification is currently in progress and is measurable. There is quite a few time series. One is illustrated here. The green line on the panel on the left shows pH at hot, and despite the fact that those time series are not very long, it's clearly the oceanification can be measured. The red line is CO2, the atmosphere measured at molar level. Very high confidence also that reducing CO2 emission will slow the progress of ocean acidification. And this plot on the right-hand side is from the IPCC R5 Working Group 1 report. The 2 extreme scenarios considered there, RCP 2.6 and RCP 8.5, show that reduction of CO2 emissions, as included in RCP 2.6, really slows ocean acidification. So there is really something we can do about that. And the third statement for the chemical aspects is that the legacy of historical fossil fuel emissions will be felt for centuries. As you can see, the RCP 2.6, there is a slowdown of ocean acidification, which levels off and then starts to recover, but it will take hundreds of years, if not more, before we go back to the pH of the pre-industrial times. The biological response, a series of high confidence statements that cold water coral communities are at risk and may become unsustainable. Some plants may benefit, such as seagrasses and several fleshy algae, may benefit from the increase of CO2. The combination of ocean acidification and warming is quite deadly on some species. Many organisms are synergistically affected by both ocean acidification and warming. Mollusks are among the most sensitive group of animals. Coral reef erosion will outpace coral reef building due to the combined effects of warming and acidification. Impacts on biodiversity are not well constrained, but information collected in CO2 vents by Paul Spencer and colleagues shows that on this plot here, the black dots are the number of taxa remaining, and here it's the pH reduction. So if you look at the pH reduction of 0.5, you see that about 60% of the taxa are remaining close to CO2 vents, meaning that 40% of the taxa have been lost. And for calcifying organisms with a pH reduction of 0.5, about 60% of the species are gone. And that includes only the effect of acidification, of course, because this is cold water CO2 vents. The biological response, now a series of statements with medium confidence that ocean acidification will adversely affect many calcifying organisms. There are many exceptions. That's why we gave this medium confidence for this statement. Theropods are already dissolving, and there is a recent paper showing that's the case along the coast of North America, along the Pacific coast. Ocean acidification may have some direct effects on fish physiology, behavior, and fitness, and this is a big surprise for me. I mean, and there is an increasing number of papers showing that, in fact, fish can sense changes in pH that are relatively slow. Just 2 weeks ago in Science, a paper was studied that some kind of fish was able to detect a change in pH of 0.1 unit. It's quite amazing. So here, I think we may have surprises in the future. Nitrogen fixation of some cyanobacteria can be stimulated by ocean acidification. And then we turn into the last group, societies and economies. And here is where the level of confidence gets very low, medium to low. The impact of the decline of shell fisheries will lead to economic losses, but the extent is uncertain, medium confidence. There will be negative socio-economic impact of coral reef degradation, but again, the magnitude of the cost is uncertain. And low confidence for the last two statements that ocean acidification will affect top predators and fisheries, and also will alter biogeochemical cycles at a global scale. Again, low confidence for that. I mean, the literature is quite conflicting. So what can be done? So I use this figure from Ken Caldera, which I think illustrates very well what can be done. the basic premises is that we have a desire, all of us, to improve our well-being. And by doing that, we consume goods and services. And to have those goods and services, we use energy. This energy leads to CO2 emissions and then an increase in CO2 in the atmosphere, leading to climate change and ocean acidification, which have impacts on humans and ecosystems. And in fact, we end up with exactly the opposite of what we would like. We want to improve our well-being, but those impacts on human societies and ecosystems, in fact, negatively affect our well-being and will affect our well-being even more in the future. So what can we do? We can conserve the goods we recycle. We can produce goods with more efficient industrial processes, consuming less energy. We can use low carbon emissions energy technologies to produce those goods in order to reduce the CO2 emissions. And once the CO2 is produced, we can try to remove it or to store it somewhere. That's CO2 removal. And once CO2 in the atmosphere, solar engineering has been proposed as a way to limit climate change. But it's very important to realize that this has almost no impact on ocean acidification, because the goal of this solar radiation management is to continue releasing CO2 without increasing temperature. But the CO2 will be released, 25% of it will get into the ocean. So not very useful in the context of ocean acidification. Then we can adapt to the changes to the climate and to ocean acidification, and we can also try to strengthen the resilience of coastal systems mostly. And once the damage is done, we can try to repair the damage. So I think this graph that Ken has put together is quite nice because it shows the whole thing, you know, from human systems to climate change, ocean acidification, and the impacts on ecosystems. Right. So to conclude, very briefly, so the drivers of ocean acidification are the burning of fossil fuels, cement production, and land use change, leading to increased atmospheric CO2, the lower pH, lower carbon ion concentration, and higher acidity, changes to organisms and ecosystems, that's what I described, the biological responses, leading to socio-economic impact. And you see at the bottom there is a range going from high certainty on the left to low certainty on the right. So the socio-economic impacts are not certain at all, and the policy options for action are listed here, and there is a hope that the climate conference in Paris in 2015, COP21, there will be some decision taken with respect to CO2 emissions. The gaps, multiple drivers, that's a major gap. Only 20% of the perturbation experiments published so far have addressed multiple stressors, acidification, and another one, such as increased nutrients. Evolutionary adaptation is also a major gap. There is progress recently, but the progress is very slow. Those are very challenging experiments to perform because they are long-term experiments. There is most of the studies have been performed at the level of organisms, studied in the lab, and there is a need to study communities in the field. Nutritional equality is an issue. Food web, how the changes triggered by ocean acidification propagate through the food web to top predator. And the fish, I think we have the work by Phil Munday and others is quite nice. And although initially I felt that fish would be completely resilient to ocean acidification, it seems that many of them are not, and there are some processes that are quite affected, even by a small change in pH. So it's
that's the thing that we need to look for. And the asterisks here show that gaps which were identified 15 years ago. So maybe OA is a soil science after all, I don't know. But clearly, this is very challenging to study multiple drivers and evolutionary adaptation. Two last slides. One to highlight the key role of IMBeR in the development of ocean acidification research. By the launch in 2009 of the SOLAS IMBeR Ocean Acidification Working Group. This group, in 2 years, established a program of activities to support OA capacity building, science, and dissemination. And the group successfully managed to collect $2 million to launch the Ocean Acidification International Coordination Center at the IAEA in Monaco. And just last week, Secretary Kerry announced that the State Department will provide $350,000 more to the OAICC. And in the meantime, the OAICC is still supported by IMBeR and SOLAS through the SOLAS IMBeR Ocean Acidification. So if you are interested in ocean acidification, I really encourage you to go and have a look at the OAICC website at the address indicated below. There are fantastic resources provided for free. A news stream with maybe 20 blog posts every week. We publish the database that we collect almost every day. Presently comprises 100 papers, and it's available through Mendeley, free of charge with the abstracts and keywords, etc. Data management is performed by the OAICC, expert workshops, training courses, and intercomparison exercises. We make use of these resources. Thank you very much. I'd like to thank the co-authors and referees of the IPCC and IGBP IOC score assessment reports, IMBeR and SOLAS for the strong support they provided, the OAICC, and also funding from the European Commission and the BNP Paribas Foundation. Thank you very much.
Thank you very much, Jean-Pierre. We have time for some questions.
Thierry from Marseille. Hi, Jean-Pierre, thank you very much for your talk. You talk about the link between acidification and nitrogen fixation. What kind of link?
This is the first three experiments which were performed. First two experiments performed on Trichodecium showed that the growth of Trichodecium was stimulated by elevated CO2, and therefore that the nitrogen fixation was stimulated. And but recently there was a nice paper, I forget the name of the first author, but from experiments performed at HOT, which the two first experiments I was talking about were performed on cultures in the lab. And the HOT study on natural communities, I believe, is questioning this simulation of nitrogen fixation. That's why overall we get it in the medium confidence level. It's still not clear what will happen with nitrogen fixation. But I believe that Andy Riss, who is at this meeting, has data from the Mediterranean showing a stimulation also in nitrogen fixation in an mesocotton experiment he performed in Corsica. So maybe you can check for Andy Riss.
Additional questions for Jean-Pierre? No? Oh, one. There's one.
Thank you for the talk and all the work you've done. On your last slide where you talked about that ring of the drivers, the link, the assumption, the first link was for well-being to be driven by the consumption. And that is a driver. But I'm surprised you didn't put the sort of white elephant solution in there, and that's population and the philosophy that consumption equals happiness. Don't you think as a community we ought to at least put that out there?
Yeah.
It's a touchy situation.
Yeah, the increase in human population is certainly an issue, and the improved well-being is not necessarily based on increased consumption, but that's, I guess, from the main CO2 emitters, which are the US, China, and India, the improved well-being is related to increased consumption. That's, maybe we can debate it, but that's unfortunately it's a fact. But you have a point, yeah.
Okay, any more questions? Okay, thank you, Jean-Pierre, for that. All right, so now we're going to move on, and I'm going to turn it over to Eileen, who is going to provide an introduction to the IMBeR synthesis and future directions and lead some discussion.
Thank you. Just before coffee break here, I'd like to talk a little bit about the development of a future plan, or the plan for the future of IMBeR. And so what I'm going to go through here quickly is to talk a little bit about the vision for the future that's come out of the information that we've received so far, and then what we are intending to do to move forward with this. All right, so very briefly, I'll talk a little bit about IMBeR science. I'll show a couple of the same slides I showed yesterday because they're relevant to the discussion that hopefully will come in the next day or so. Talk about the potential science themes that have emerged from the information that we've received from input up to this point, and then the process of developing a plan for the future. All right, as we've heard several times yesterday and this morning, IMBeR is structured around these 4 research themes, which Raleigh mentioned this morning. We heard presentations on the first theme, which is the biogeochemistry and food web interactions with Coleen, the sensitivity to global change from Nikki and Jean-Pierre, feedback to the Earth system in responses of society. And also, I should say, the coastal work that KK talked about yesterday goes through all of these. These things are not independent. They do, in fact, have much in the way of overlap. All right, and to remind everyone, IMBeR does its science or its activities through these regional programs, and there are 4 of them right now. And the working groups, as we've heard, the importance of the soil off IMBeR ocean acidification working group, the carbon working group, continental margins, yesterday KK's presentation, and also data management capacity building run across all of this, and then the joint working group with Clive on. All right, so IMBeR has these working groups that have these regional programs, but the yellow dots on here are the national programs or endorsed programs from IMBeR. So that people in their own organizations, national programs, countries, or whatever, develop something that does research that's directed at IMBeR science themes. And a lot of the science is done in that way. And so what you see here is the distribution of the endorsed programs or the national programs that we have for IMBeR. All right. The other thing is that this is all coordinated through a regional project office, which is in Shanghai, China, at East China Normal University, and also the international project office, which is here in Bergen at the Institute of Marine Research. Okay, so as we've heard in the presentations yesterday and this morning, IMBeR has made a lot of progress in addressing its research themes, but IMBeR is approaching its 10-year mark, and it's time to think about these, see where we have, what we have done, where we have come, and how we would develop this next phase of research. All right, and programmatically, as I mentioned yesterday, one of the co-sponsors of IMBeR, the IGBP, will be ending at the end of 2015, and it's being replaced by, or being folded into this, the Future Earth, which we'll hear about tomorrow from Coleen Moloney in her presentation. And IMBeR has been invited to participate in Future Earth, and we'd also like to put together a request to our other co-sponsor, the Scientific Committee for Oceanic Research, to have another 10-year program. And we're hoping that we can submit that in fall of this year. Okay, so as I said yesterday, we solicited input from regional programs, working groups, anybody that would provide input. And we've used that input to try to outline the key issues and challenges relating to the ocean and global change, and from that, and how IMBeR can address these in the next 10 years. And we've already heard a lot of new and exciting developments that we build on what IMBeR has already done. All right, so we put together this information, and out of that, there are 5 potential research themes that emerged. And those have been developed into a draft position paper, and as I said yesterday, draft is very much that. And for each of these themes, we've come up with a challenge, a rationale for them, and a little bit of an approach for how they might be addressed. All right, so what are these research themes? Well, the first one is the continued integration of biogeochemistry and ecosystem research. And I thank Coleen for really setting this up well. We've done a lot, but there's still a lot more to do. There are many gaps in understanding, and as Coleen said, there's a tension between understanding and prediction. So there's still a lot to be done there that will build upon what we've already done. The other is to look at the impacts of climate change and climate variability. That, again, has gone through all of the presentations we've heard already. To look at, as Jean-Pierre just pointed, multiple drivers, stressors, and responses of society. And things don't occur in isolation, as we said. And then the integration of marine biodiversity and conservation. And this is this would be a new direction from IMBeR, but it would build upon what we've done up to this point. All right, and then the integration of ocean-human systems. All right, these themes are not independent. There's a lot of overlap between them, but they each have their own aspects. All right, so a little bit here is the theme 1, the biogeochemistry and ecosystems. The challenge within the position paper is to develop end-to-end approaches for predicting the effect of change on marine ecosystems and human societies. And this nice diagram here is from one of Coleen's papers showing all of these interactions. And at the time this was done, the biodiversity and adaptability was one of the things that was highlighted as what's missing from many of the models we have right now. All right, so this rationale is that questions remain about the coupling of biogeochemical cycles and food webs. And also, we want to be able to use these models to evaluate responses of ecosystems to change. Theme 2, the global change and climate variability. The challenge here is to decipher the multiple interactions between the climate system and the marine realm and their sensitivity to environmental change and climate variability, and eventually to get to predictive understanding of future responses and interactions. And the figure down here is a projection of sea surface temperature at the end of the century. And as you can see, the high latitude areas are undergoing a large amount of change. So what is the implication of, or effect of these kinds of projected changes on our ecosystems and the marine systems. All right, so however, the rationale here is that the global and climate changes are not uniform. There are variable physical and ecological effects, which this type of diagram would imply. And what we want to be able to do is to provide projections of future states and future change that also include socio-economic effects as well as the changes in the marine ecosystem. All right, theme 3, the multiple drivers, stressors, and human responses. Right, and the challenge here is to undertake integrated studies of social, ecological, physical systems to consider interactions of the multiple drivers and stressors within a given environment and consider the various scenarios for change. I think that's one of the things that I've been hearing a lot at this meeting is the development of scenarios and using those to guide future directions. All right, so again, the drivers and stressors do not occur in isolation, and the potential risks may arise from new frontiers for exploitation for marine resources. And this is from the presentation that KK gave yesterday. That's something that we need to think about is how we're going to be using our environment and our natural resources. Theme number 4 is marine biodiversity and conservation. Again, the challenge here is to provide evidence-based information and scenarios that help protect and preserve the marine ecosystem biodiversity and improve management of resources and services, limiting damage to vulnerable marine species and restoring marine ecosystems. And for here, biodiversity, the rationale is that it determines resilience and response of the ecosystem to change, and also it's linking ecological and genetic studies to understand the ecological responses to change. And this is something that has been a great deal of progress made in this area, but it's something that the models don't do well, and I don't think we understand well enough how to include it as part of future projections of the responses of marine systems. All right, and the last thing here is the human-ocean interactions, and this is to explore linkages and interactions between ocean systems and human systems, maintenance of those, coastal communities, economies dependent on marine sources, and trade-offs with conservation of ecosystems. All right, so again, the rationale is that global change issues are social and human issues, and humans are the driver and the recipient of environmental change. And I think that's been brought out in many of the presentations already. All right, so those were the 5 themes that emerged from the information that had been provided up to this meeting. And these are simply put there as a way to begin our discussions about future directions for IMBeR. All right, the other part of this is how do we do this? How do we facilitate research? All right, and observation monitoring networks are certainly that an important part of that. And there are any number of systems here, but since IMBeR has started, there are new technologies, the autonomous types of instrumentation have really developed, and more innovative approaches to how we measure the environment. And how would these be brought in the next phase of IMBeR to help address the research questions? Human networks and capacity building. Right, that's a very important part of IMBeR is to develop the community that can successfully implement the research questions or assessment. And then also data management, which has been a central part of IMBeR since its beginning, and how we expand this and improve IMBeR data visibility in neurosciences. All right, these 3 things integrate all aspects of IMBeR science that go across all of the 5 themes I just talked about, or for that matter, any themes that are developed. The other thing is the way the program is structured right now. We have an international project office, and that provides coordination and management and assists with funding for activities, and it provides communication. It's a very important part of the program. We also have the regional project office that provides coordination and assistance in specific areas. And the regional project office in Shanghai is very effective at helping promote IMBeR within the Asian community. All right, and then there's a science committee that's composed of individuals that with expertise relating to IMBeR activities, and these people provide the liaison with the scientific community, and the membership of that committee changes depending upon what the focus of IMBeR is at any one time. And they're anywhere from 14 to 16 or 17 people on that committee. All right, so this is the current sort of structure we have, in addition to the regional programs, the working groups, and all that. But should we consider different structures? Right? Is there a better way to do a project like IMBeR? And I think that would be a certainly fair thing to discuss. All right, one of the questions we asked when we sent out the request for information is, what do you get out of a program like IMBeR? All right, what is the value added of having a global environmental change project like IMBeR? All right, and the response is sort of broken into two areas, and I've only put down the main ones here. The first one was in terms of the science, all right? So that projects like IMBeR enable global comparisons, cross-fertilization of new ideas and approaches between countries. It's a platform for discussion about various aspects of global environmental change, and it also helps promote capacity development. And you move forward in particular areas of research through programs like IMBeR a little bit more quickly than you would if you're depending upon individual scientists to do things. An example I'll use is from GLOBEC, where GLOBEC really advanced the use of coupled physical biological models. That probably would have happened anyway, but it certainly would not have happened in the way it did without this overarching umbrella. I think what we've seen here with the ocean acidification work, the end-to-end food model, and food web modeling, and the understanding of carbon cycling in the ocean, IMBeR has advanced all of that, I think, as a program, and it's advanced it a little more quickly than it probably would have done with individuals, or a single individual science. The other is programmatic things, is that a program like IMBeR provides a framework and a justification for institutional, national, and regional research initiatives. It's a mechanism for synthesis of research from various institutional, national, and regional programs, and it also helps to leverage funding. You're part of a larger community, so it sometimes makes it easier to do that. All right, so here we are at our Open Science Conference, and this it provides the opportunity to update our research agenda to guide future research into marine biogeochemistry, ecosystems, and the human dimensions of global change and the interactions between them. The conference here is a mechanism to gather information or input about future research, and also future research directions, and to highlight these new and exciting directions. All right, so the process we have here is that we've allocated time at the Open Science Conference for breakout group discussions, and they will be tomorrow morning. And each of those will be structured around one of the 5 themes that I mentioned here, as well as one on capacity building and also data management. We very much encourage open discussion, open consultation, because this is the opportunity to define the next phase of IMBeR research. And I particularly encourage the early career scientists who are here to be engaged in this and to participate, because this could in fact be an important part of your longer term career. So please get involved in doing this. All right, the results of the breakout groups will be provided in a plenary session on tomorrow afternoon. We'll use all those inputs to revise this draft position paper, and then it will be provided again to the community, which I'll show here for continued discussion. And then we're going to use within that to form the basis for the extension request that we'll send to SCORE, and also for the request for the transition to Future Earth, assuming that's what the community wants to do. All right, so how do you provide input? Well, part of it is you have your discussions here, but there is a website set up where you can go in and actually enter your input to it, where you submit your input on the IMBeR position paper, and you do it either as an individual, a representative of a group, an institution, it's signed, however that is, but this is available and set up for input. All right, and then this, as I said, the paper is going to be discussed and revised during the Open Science Conference, and we'll use the input we receive here to do this. And this will, we will attempt to, whatever input is already there, we'll attempt to have some of this available to the breakout group leaders tomorrow to help inform their discussions. All right, so as I said yesterday, IMBeR is a very strong research community with a focus on marine biogeochemical cycles and ecosystem responses to global change. All right, we are already bringing together the natural and social sciences, and our science has expanded beyond what's in our original 4 themes. So we can improve this by identifying new directions and needs and developing an implementation approach for these. And there are opportunities there for many new, exciting, and different research directions. So I'll stop at that point, and I'll thank you in advance for your input and for your help in defining and setting up what would be hopefully the next phase of IMBeR research. So thank you.
Any questions for Eileen about the process that we're going to undertake? Or anything else?
You mentioned that the position paper is a draft. Do you also consider the research themes? You identified 5. Are they also rock solid, or they are?
Oh no, they are draft. I mean, and if the decision here is we're going to throw the 5 out and come up with 3 more, that's fine.
The question I'm asking is the impacts of global change are distributed across several of those themes. I don't see the distinction between some of them. Perhaps this needs to be clarified, maybe by changing the title of the theme, or maybe by.
I agree with that, and that's fine. If you change the title, the direction, it's fine. These are simply a way to get a conversation started.
Another question for Eileen.
Thank you for your very nice presentation. And I have 2 comments. One, that if I want to visit for answer this, and the second comment is okay.
Your first comment was more emphasis on society,
societal relationship between science and society. It is starting with moving, but I think we like it out. The larger structure that is proposed
to foster the interaction. Yeah, I think that's very true. And I think IMBeR as a project has made a lot of progress in that direction, but there's still much more to be done.
The second, I remember, was working the relationship between IMBeR and Future Earth. Hierarchical.
Okay, so Future Earth is an overarching organization or structure, and IMBeR would be a core project underneath that larger structure. It would be similar in many ways to the structure we have now, where IMBeR is a core project of the IGBP and SCORE. And IGDP is being replaced by that. We'll hear back to you.
On the left here.
And thanks for the nice presentation. And maybe I missed this. Why not have the direct provision of scientific advice that is understandable scientific advice to decision makers be part of an explicit part of the value?
It could be, and that is hidden. If you read the text underneath the fifth theme here, the ocean human integration ocean, there are words connected to that. It maybe you should be up there.
We had a couple of questions over here first.
My name is Jean-Pierre from China. I propose a kind of new research, new direction. What is it? Okay. Ocean carbon sink is a new direction for English for a number of reasons. First of all, it can be ocean carbon sink can be a parameter for low carbon economy. Because now we have lots of ecological structure problems, which is caused by river linkage, like using plastic. Now, it's going to have a physical policy for that. It's actually the penalty for the city. If you have ocean carbon as a parameter, as a kind of scientific evidence, we can propose some new policy, which is penalty. So we can encourage people to use plastic. We can think as a parameter. And then in the future, we can use the ocean carbon for carbon trees. So those kind of reasons that the ocean carbon can be very important. And which is also closely related to future Earth. So it's the connectivity of the water.
Well, I think that's part of the discussion we want to have.
Thank you, Eileen. Just a quick comment is, will instructions or directions be given tomorrow as to how to orchestrate the breakout groups?
We have, yes, we have, people have been identified who will lead the breakout group. And tomorrow we have a 15 on the agenda. I'll put that out there. And they had some discussion with them about that.
Thank you. I was thinking more in terms of how people decide which.
I'm sorry. Yeah. Well, I'm hoping that people will self-organize and go to the groups that you are interested in, or like to contribute to the yeah. Otherwise, I could go to the plenary session tomorrow. I can go around and 1, 2, 3, 4. See if everyone can remember your number long enough to go to a breakout group. But I would prefer it to be self-organization.
Question about.
This got a question for the women. We've got a huge emphasis on social economics. How many of you here are actually working or consider yourself someone working in social economics? Okay. I'm having a hard time finding people who work in projects. Yeah, thank you.
And I think that's one of the indicators of success is that more than one hand went up. So I think IMBeR has made progress.
Thank you, Eileen, for your talk and for leading this difficult task in the future. One of the key issues in Future Earth is the link with stakeholders and actors in the society, making science with actors like NGOs, global institutions, but also the private sector. how would you foresee the link of IMBeR with non-scientific actors in the future?
I think we would have to figure out a way forward. That's not something we've done, but that doesn't mean we can't do it. We just have to figure out how to do it.
Any other questions or comments for Eileen? Oh, there's one over here.
Thank you very much for the talk. For the facilitating potential of IMBeR, I would like to bring in the modeling. I mean, it has been made an attempt in the past of erosions, I think it was, to find a maze through all the models available. But I think meta information about models and distribution of models and making them available to other people is also something next to observational networks, and which it should be thought of. It's terribly difficult, but there are some experiences, especially from the global Earth system modeling. We'd like to encourage that to learn from this and to bring this more forward to more limit in more specified models.
So you would say that with the facilitating research, there should be something at the bottom and calling it out directly. Yeah. Okay, that's a fair comment, and we had initially thought about that because in looking at the input we got, models would across everything. So yeah, that's a good comment.
Any other questions or comments? That's good. So cutting the break.
All right.
So thank you very much.
Thank you very much.
One more. Excuse me, hello. I have an announcement to make. Posters that were put up yesterday for the Tuesday session, they have to be removed now to the coffee break, please. And the poster for the Wednesday session today can be put up by lunchtime, starting lunchtime. Thank you.
And if I could also just say, those who are involved in the Lunch for the Scientists for the mentoring program, please will you go to the restaurant upstairs. That's been reserved for today and tomorrow. Thank you.
Just a clarification about that. Yes. Did you get